This afternoon, I want to talk about vacuum PVD improvement, the concepts and some applications. This is the one that Dr. Sotisak introduced me. And I also belong to the top 2% scientists that together with around 7 faculty members of EIT, which, by the way, everybody has retired. So I hope EIT is still doing well to catch up with us. And this is my pioneering book, Soft Ground Improvement, where I place everything inside, like drainage, PVD, deep compaction, then reinforcements, and then mixing. Reviews to that. Each topic has its own as one book, but I put them together into one volume. And this, and in the right side is front page of the Google Scholar under my name. Bangkok clay is quite homogeneous in the sense that there is no sand lenses in the middle or silk lens, which are quite, there are some lenses but negligible. So we can call it homogeneous, thickness from 10 to 20 meters, which is quite good because good subject for research. So it's known the whole world that we have a lot of deposit here. Properties is well known because of so many research works. This is a profile of the water contents, which can exceed 100% because of some around 5% of organic matter. This is the undrained strength, which is around 1 ton or 10 kPa. Usually used for parameter for design. But there is under pressure because of the withdrawal of groundwater at the underlying sand aquifer. So there is a piezometric drawdown starting around 10 meters. So for a while, PVD were not used in Bangkok because of this. When I arrived in Bangkok, that is the big issue, that if you put a PVD, it will increase the rate of subsidence because of the drainage from the clay to the sand aquifer. If you put PVD, it will increase or enhance the drainage down below. So I solved that one by putting only the PVD at the upper 10 meters. As of now, when we had the project at Suvarnabhumi, the third runway, the drawdown is still there, around 12 meters. So that's why we put our drain around 10 meters depth. So it has not been recharged. So that even though the deep wells are not allowed anymore, but still the existing deep wells are still allowed to function. So these subsidence will have differential settlement between the piles put, for example, columns, and the surrounding ground. That's the cause of subsidence. Then we look at the soft clay, and the soft clay is quite soft with a lot of voids. The solid sometimes only 40%. So to improve it is to reduce the voids In order to reduce the voids, you have to remove water. It's called dewatering. But this one requires time because the permeability is quite low. So that's why the importance of artificial drain like the PVD. If we just load it like the traditional, we'll just put a surcharge. The drainage path is quite long. So this process tends to be very slow, about 10, 20 years. Then if we install an artificial drainage like the PVD, then the drainage path is shortened only by the spacing of the drain, and the main drainage is horizontal instead of vertical in the previous one. So the horizontal permeability usually larger than the vertical permeability because the clay is sedimentary deposits, sediments. That's why if we put PVD, we have to install a PVD first. And the conventional method is to apply a surcharge, embankment surcharge, to create hydraulic gradients so that the water will flow through the drain from the clay going up against gravity. That's why somebody asked me, how can you drain with a PVD when it is against gravity? And that's why due to the surcharge creating an hydraulic gradient. And usually before when we have done test embankment at Ronapom Airport, we put a berm to prevent side slope failure because of the clay is weak. So without drain, take some time to drain to achieve 90% degree of consolidation. With vertical drain, it will be faster. We add vacuum, it will be more faster. And then there's a question, why you put vacuum? It increase the cost. But the time will be reduced, and time is money. So the cost of vacuum overall will be the same as the conventional if you count the time of preloading, which is shortened by the vacuum PVD. So the PVD is composed of channels of flow with a core and surrounded by filter. And the channels of flow, the core, serves as the channels of flow and prevents buckling. The filter minimizes the entry of clay particles into the core so as not to clog up the channels of flow. That's why I'm wondering why some researchers still insist of using jute drain or fiber drain without channels of flow. How can the water go up? And they said it's due to osmosis, but it requires some channel flow of the water from the clay up vertically to the drainage. And so the PVD can be arranged in a square or triangular pattern. And the square is a little bit inefficient. The diameter in such assigned to one drain is around 1.13 times the spacing. Triangular is more efficient, is 1.05 times the spacing. However, the square pattern is easier to lay out in the field than to control. That's why most of the time square pattern is used with not much difference in a way. And if you only have to install about 10 meters, so you just need some kind of a modified backhoe. Unlike in Singapore where they put 40 meters, then you need a special equipment. Of course, there are also special equipment used here, but and this modified backhoe is good enough. Since you put something into the clay, then it creates a disturbed zone. This disturbed zone or smear zone have lower permeability KS than the original KS. So this can be served as a barrier of flow of the water to the PVD. Here, QW is vertical discharge capacity of the PVD. And there's an equivalent diameter of the PVD and equivalent diameter of the smear zone, DS. And big D is a function of the spacing. So to minimize or to accelerate consolidation, there's a lot of research in the smear zone. And one of that is using vacuum, using electro-osmosis. I use heating the PVD here. So a lot of doctoral degree obtained by just looking at how to minimize the zone of disturbance or to mitigate the smear zone. Now with the vacuum, increase the, means we put in a vacuum pump, connect to the PVD rather than the surcharge. And that case, we don't increase the load, rather than we reduce the pressure. And then in that case, increase the effective stress. So in that case, instead of surcharge alone, we put surcharge combined with vacuum, atmospheric pressure. And then that will reduce the pore pressure and increase the effective pressure. And we can have some kind of benefits. So if we need 70 to 90 kPa preloading, it's better to combine surcharge and vacuum. And after vacuum, the surface elevation will be of the treated area will be lower. And we add environment construction and save construction time. There will be a lateral movement. So there is some inward lateral movement, cause some cracking. But the cracking, most of the time is about 6 meters beyond the boundary of the membrane. So it does not interfere with the vacuum, the cracking. So here are the selected vacuum papers that I and my research students and staff have published since in 1998. This is only Vaccuum-PVD. PVD only, there is more. So we have now around 16 for a span of around 20 years, from 1998 to 2021. So the ground deformation, I get this one from Professor Chai, my previous student, who is now in Japan. Without vacuum, we have the vertical pressure and the lateral pressure, which is a function of K naught times the vertical stress. Before, when the pressure, lateral pressure is higher than the vacuum, there is no inward movement. But if the vacuum is larger, then there is inward movement. And that causes some cracking in the ground. Means the vacuum is larger than the horizontal movement or stress. The vacuum stress is larger than horizontal stress. And then Professor Chai has coined an in-between active and at rest pressure is called KAO, which is a function of beta, empirical factor. Use that here, KAO, to assign or compute the horizontal stress. So we proceeded to compute the vertical deformation and the horizontal strain or lateral displacement, a function of B here, half width of the treated area. Then that can be summarized here. We have condition for inducing lateral displacement, then creating a tension crack. The tension crack depth is also obtained here. And then the strains can be vertical and horizontal strain equations. So he applied to a storage station in Tianjin, China. This is the swell profile. Then confirm that the measured is inward movement measured in closed circle and triangle. And then the predicted or simulated using beta 0.67 or beta equals 1. And the agreement seems okay. Another one is in the airport site in China. And here you have a measured in solid line and calculated using beta 0.67 and 1 and good agreement there. He also combined vacuum with embankment preloading. This is also from Professor Chai. In the vacuum at the top of the drain is higher than at the bottom of the drain. And this is confirmed from our measurements. And he got some equations for the equivalent permeability. Here, equivalent vertical permeability, KV1, as a function of the horizontal and vertical permeability and the flow of the PVDs, which is a function of spacing, smear, and discharge. So for 2 layers, we also have equation here. So for the project in Saga, Japan, this is the soil profile. And the loading, vacuum pressure with time, varying pressure with time. This is the settlements with depth. The profile of settlements from the center to the from center line of the embankment, more at the center than at the side, and the movement, inward movement, and measured and simulated. So there is a theoretical simulation of 3 cases. One, you already have the embankment and you apply vacuum. Second, you only have the embankment. Third, you have the vacuum, then increase the embankment height. So for lateral movement, the one with embankment only, case 2, is the dashed line here with large outward movement. And the one, case 3, this one, vacuum first with embankment, there is inward movement. But the embankment first with vacuum, there is still some outward movement. This is in a vacuum and then after 6 months. While the settlements, of course, the case 1, case 2 and case 3, almost the same, but case 1 is larger. Now we have done work before in Sonapum, where we have direct connection of PVD to the vacuum. And this was now abandoned because there is some stiffer contact here connection between PVD and the tube to the vacuum pump. So when you have large settlement, they tend to have some leakage here. But it has been done. This is for conventional PVD with, in our case, we have done at Sonapum or a 4.2 meters high embankment. But with vacuum, it's only 2.7 meters. Now you can use only 1 meter. And you see the vacuum pump is around 80 to 90 kPa. This is a settlement between conventional and vacuum. The conventional here have 2 stages because of stage loading. This is the vacuum. See, when you put vacuum, then you can save some time to 90%. This is in the field. And I have done work at the lab. We have a model loading, large consolidation equipment. This I brought from Japan and I modify it here. So we put some air pressure as a surcharge. Vacuum can be applied to the PVD. And this is the comparison between vacuum and normal PVD. We have some faster settlements for vacuum. Then we have the Dr. Sompot at King Mongkut, Thornbury. He has designed this equipment here, this side, loading with vacuum, this one loading without vacuum. And I put my student there, do the experiment. This is a huge equipment. And we have this one, PVD and PVD with vacuum. You can see the accelerated settlement using vacuum. This in the lab, in the field and in the lab. And then I have made another test, identical equipment, one PVD only, one with vacuum and one with vacuum and heat. You can see here the smear zone. The PVD is here. This is smear zone. The shear strength, when we have PVD only, the lowest, we have vacuum PVD, a little bit increased in shear strength. And there's a vacuum, a thermal PVD and thermal vacuum PVD, much larger increase in the strength, especially at the smear zone. And this is the results. The PVD only, vacuum PVD, and the thermal PVD. You see thermal PVD. There is no more secondary consolidation, secondary settlement. So it is much faster than either. And the problem is how to put the heat in the field. In the lab is easy, but the field requires some. But some other researchers now you apply the heat by using plasma to clean up the waste disposal area. That some of my friends told me it was very successful. I also look at the micrograph using SEM. And this is the micrograph before vacuum. You can see the face-to-face arrangements. But after vacuum, you can see the edge-to-face arrangements. And you can see then that because of this, the strength larger, permeability is higher. So this is called a flocculated structure. So there's an explanation on what happened when you put drain, vacuum, PVD, and vacuum PVD with heat, heat with PVD. It also changed the microstructure of the clay. So back to vacuum PVD with airtight membrane. So we have PVDs here, connect with horizontal drain, horizontal drain connect to the vacuum pump. This is the scheme we have at our Hino test track project. You can see the PVDs here and membranes, horizontal drain, and the pipe going to the vacuum. And the PVDs with horizontal drain. And you have the airtight membrane. You have the filter to protect the membrane, I mean the geotextile. The horizontal drain is also a bigger drain. And then we have there the canal excavation where we put in to seal the membrane. And the cracking is outside, about 6 meters from the canal. So this is connecting to vacuum here. Then all the instrumentation. These are more clearer. This is the PVD here. And strip drain for horizontal drain. Geotextile, first layer, second layer to protect the membrane. They have also the third layer, geotextile, to protect. And then we have this one, the air water separation tank. This is the horizontal PVD connected to the horizontal drain connected to the PVDs. This is the connection from the PVDs that connect to the vacuum. This is the layout, geotextile and geomembranes. Geomembranes protected by geotextile below and above. And there is water coming out when the vacuum pressure is started. This air water separation tank is distributed in the field to be more efficient in applying the vacuum by taking the water out first. So this project is around near after the Somanapom Airport. Sorry, the location should be around here. At some industrial estates. These are used by Hino Motors for driving the trucks around here, around this. And so we divide into zone 1, zone 2, zone 3, zone 4, zone 5, zone 6, together with the boreholes and the field main tests. So you can see here the horizontal PVDs, the horizontal drains connected to the PVDs, the installation of the PVDs. I was there, so they took my picture together. Soil profile, you can see in Bangkok, soil profile of very soft to soft clay around, and that place is around 17 meters. There was a surcharge field. And so the length of PVDs were 17. That area, the drawdown is negligible. We are near the Bangpakong River. So we put it to the whole length of the soft clay. Triangular pattern, spacing 0.9. Surcharge 2 to 3 meters. So these are instrumentations. We have oximeters, single, double settlement plates, and inclinometers. As I say, soft clay is 17 meters. Embankment average 2.5 meters thick. The vacuum around 80 TPA, and we have piezometers, single and double. In the middle of the clay, we have around 60 TPA. This pore pressure at different depths, decreasing slightly with it. The settlement for each zone, zone 1 to 6, different settlements because of different compression modulus of the clay. This is rate of settlement in millimeter per day. We stop vacuum around almost lower than 5 millimeters a day, 2 millimeters a day. Around 90% degree of consolidation, rate settlement not more than 5 millimeters per day. So we can get from observation of settlements, we can predict maximum settlements by Asauka or by hyperbolic method. The Asauka is more reliable because it comes from the actual shape of the settlement, while hyperbolic assume that the settlement curve is a hyperbolic shape, which is not. So the Asauka is more reliable. So for zone 1, this one, zone 6, zone 3, we have ultimate settlements from Asauka. And consolidation by Hansmo method. We have all the parameters here. This is the degree of consolidation combining horizontal and vertical from the, then getting the DE from spacing, equivalent diameter of the PVD, and here the smear zone, which from my research before, around almost 2 times equivalent diameter of the mandrel. There are many other results, but DS equals 2 dm, equivalent diameter of the mandrel by area, is quite good parameter. So if we use Asauka's method, we can predict CH from the slope of the Asauka plot here, the slope of this plot is settlement before and the present plotting here, SG minus 1 and SJ. And our time interval here is 20 days. This one we can predict CS value from the Asauka. This one is the settlement prediction, one-dimensional, normal consolidated clay and over-consolidated clay. Then the CH can be predicted, knowing we have DS equal DM at 2 and KS over KS. So we have around around some 4, like that, 4, Ks over Ks of 4. For PVD only, Ks over Ks could be 5. But if you have vacuum, the Ks increase, so this ratio will be smaller, like 4. Then we can get Cs value. And so on for other zone. This is zone 2. This is zone 6. Because as you can see, the settlement here we have over consolidated, normally consolidated. So we have CR and CS here. Then we can have the observed settlement for each zone 1 to 6. The Asauka method ultimate 1 to 6. So we can get a degree of consolidation all exceeding 90%. If we use the one-dimensional consolidation, we have these values. And if we use that, we have the DOC also more than 90. We can compare this to the Asauka method. And the requirement was more than 90. And there was a rebound. The rebound about maximum here 70 millimeters or about 7 centimeters. Then we compare the properties before and after. After is the colored with blue and red. Before is the lightly colored gray. So we have the unit weight increase as expected. Water content decrease as expected. The standard blue, this one is nothing, is below the improved area. And the Atterberg limits. A lot of decrease here. And there was some question from the reviewer of our paper that it should not decrease too much. The liquid limit. In sonapom, the reduction is not much. So this one here, we get this from the laboratory test after improvement. So could be some problem here because the liquid limit reduced very much. Under shear strength increase from around 10 to 20, 25, from soft clay to medium clay, medium stiff clay. Compression index change. Void ratio is reduced. OCR increase. This one here also has problem because the testing we have same as the one for the sonapom. The test they have, we cannot see the inflection of the consolidation curve. So the maximum pass pressure, this is the disturbed zone, disturbed maximum pass pressure, which is similar to the before improvement. That's not possible. This is the OCR. The maximum pass pressure here. You can see not much increase. But anyway, there is some increase. But around 10, we have around more than about 5 meters depth. We have more than 100. And that's good enough for the purpose of the test track for trucks, or the Hino trucks. The undrained strength increased much. Here, before improvement is a colored one, after improvement is the open one. As I mentioned, increase up to 30 kPa. So from the undrained strength, the maximum pass pressure can be correlated about SU equals 0.22 sigma P. So we can see that this should be more than, maximum pass pressure should be more than 100 if the increase of shear strength is around 30. 30 divided by 0.22 should be more than 100. The cracks about 6 meters away from the canal and did not interfere with the membranes up to the canal. And this is the inward movement of that's why it produced cracking. From the final element modeling, we can see that there is some plastic tensile points here at the location of the cracking. I'm about to finish here. We look at secondary compression. Secondary compression is equal to C alpha prime H log Ts over Tp, with Ts over Tp. Ts the life of the structure, Tp is the end of primary, and T over Tp usually around 10 years after. Log of that is 1. So Ts 10 times Tp, log of Ts over Tp is 1. And if H is 15, you go to 17, but there are 2 meters of fill. So the thickness only is 15. So the secondary compression, if you use this formula here, is around 30 millimeters in 10 years or 3 millimeters per year. So we have the residual settlements is equal to the remaining primary settlement, the secondary compression, and the compression below the improved layers. Oh, sorry. And these are the data. Malaysia, I have 250 millimeter, and in or 25 centimeter. In Vietnam is 30 centimeter residual settlements required. Limit of residual settlements. So conclusion, we have here the concepts of PVD been discussed, and the PVD, the preloading, the loading vacuum PVD was stopped 90% DOC with 5 millimeters a day rate of settlement. The vacuum maintained at 80 to 90 kPa, and the Ks over Ks now reduced, so we have CS values around 3 to 4, and we have increase of maximum pass pressure and OCR. Secondary compression is 3 millimeters per year, and the rebound around 70 millimeters around. So the rebound is there, but it's only negligible. Thank you very much for your attention.
Thank you, Professor Bergado. Thank you. That was wonderful speech. Okay, now we have about 5 minutes for questions. Professor Bergado, I am seeing one question on the chat box. Actually, two questions so far. Do you want me to read the questions to you, or you want to just look at the chat box?
Can you give it to me?
Okay. So the first question is he's interested in a thermal PVD and what is the temperature and which is large enough to change the thermal PVD method compared to the regular PVD, and how can we change or decrease or increase the temperature?
Yes, in the laboratory, you can put special electric wires inside the PVD, and then you connect with the thermostat. It should not exceed 100 degrees. So only around 90 degrees. Otherwise, because 100 degrees is the boiling point of water. So around 90 degrees heating.
Okay. I have a question on this slide too. So about the thermal PVD as well. So on the slide number 48, you're showing having the thermal PVD changes the rate of consolidation and also the total consolidation amount. So how does the thermal PVD change the total amount, total consolidation amount?
Yes, the heat increases the permeability of the clay. Because there is the fluid, I mean the water will flow faster when heated. There's a property, I forgot the property. There's a property of the water that can flow through the pores in the clay faster. You have to look at in my paper to see it.
Sure, I would love to. Thank you.
That increases the permeability by 3 to 4 times.
Okay, sounds good. Thank you. I have another question on the chat box here from Alan. He's asking if there's no surcharge and only the vacuum is used to apply the pressure, and how the cracks can be controlled. And also his second question is it necessary to fill up the gaps caused by the cracks so the water cannot infiltrate into the ground and increase the water pressures?
The cracks happen outside the test area, outside the improved area. And if usually in the soft ground, you have a loading platform where you put the fill so that your installation equipment can be supported. So there is always a loading platform on top of the soft clay. So is convenient. And because without the 1 meter fill with geotextile, the installation of PVD cannot be done because it's soft ground. So why you do vacuum PVD without surcharge when the surcharge is needed for the installation of PVD? That means if you don't want surcharge, you have to remove the surcharge after installation of PVD. That's impractical.
Yeah.
And because of surcharge, you can control the inward movement or reduce cracking. But cracking anyway is not a factor because it is outside the loading area, improved area.
Okay, thank you. I do have a couple of questions in the chat box. Let me ask those very quick. I know we are a little bit over. The question is, what are the practical difficulties when we apply heat to PVD? And then what will you recommend between the vacuum PVD and the vacuum PVD plus thermal plus heat?
Yeah, the most difficult is how to apply heat in the field. You can use the sun and how to devise it. So some people for clean up of garbage at the sites in the USA, George Corner told me that they use plasma combined with drainage. But when you use plasma, the temperature is very high. So you require some kind of, another kind of the vertical drain. This is not made of plastic, maybe made of steel pipes with holes, perforated pipes, plus plasma.
Okay, thank you. And then and next question is, can we reduce the effect of the smear zone with thermal PVD, with heat?
Yes, that's a part of my research. And if you can read my papers, we almost reduce it to around 10%. That is the conclusion of our result. But we cannot make a patent because anybody can do it.
Okay. Well, I remember one time you and I talked about, well, we should get going on this thermal PVD research. So if anybody who is interested in working on this topic, I guess we can continue to talk about this too. I do have another question. Sorry, Dr. Suisak, I'm bumping into your time. How do we prevent that tension crack outside of the treated zone when we actually do the vacuum PVD? I know sometimes that tension crack might not be an issue because it's on a rural area, like airport is not a big deal. However, we have a project in Indonesia. The vacuum PVD was applied to a residential area. Then the tension crack could actually affect the roads and the buildings adjacent to the treated area. So what should we do to avoid that or minimize that?
Maybe Dr. Sutisa can answer that one.
Yeah.
Well, if you increase the surcharge, you minimize the cracking. The one that I show, the earlier I show this one here. You can see that actually the inward movement is disappear after 6 months, or in a way, this one is minimized depending on the amount of the surcharge.
Yep. That makes sense. Okay.
Here, there is no more inward movement after 6 months.
I think that the best way is to have enough offset from the nearby, that of course, that's the best way. Otherwise, at the edge of the VCM, you can increase a little bit of fill in order to provide the outward movement.
Correct.
Yeah, something like that.
Okay, thank you.
All right.